Hey guys, today we're going to talk about free fall. Free fall works in exactly the same way as the rest of the kinematics problems. The only difference is now we actually know acceleration at all times. So free fall occurs when only one force other than air resistance is acting on the body, and that force happens to be gravity. So air resistance can slow an object down, but we don't actually include those because they add an extra component to our calculations. Galileo was a person who calculated acceleration due to gravity, and he noted that acceleration due to gravity is 9.8 meters per second squared. Now that number varies slightly based on if you're at sea level or the top of Mount Everest, but for our purposes we are going to keep it at 9.8. When an object enters free fall, the velocity will increase 9.8 meters per second every second. That's the definition of acceleration. Okay, so an object will increase its speed after every second it travels at a rate of 9.8 meters per second. Since our frame of reference normally equates the positive motion as going up, gravity actually has a negative value since the object is falling downwards towards the ground. Just think of it in terms of a graph or a number line. Our positives always go up and to the right, so since things are falling downwards, they would have a value that is negative. So here's an example of a free fall video. This video was taken on the surface of the moon.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Alright, so in this video they showed that in a vacuum, in space, because space is a vacuum, there are no air molecules, objects actually fall at the same rate. So had we done that experiment on Earth, they would have fallen slightly faster because Earth has a higher gravitational pull, but also the feather would have fluttered to the ground. It would have kind of waved back and forth as it fell due to the high air resistance value of the feather. So in a vacuum, objects fall at the same rate. Gravity affects every single object exactly the same way. So in this photo, a snapshot's taken at equal time intervals. It's not necessarily every second, but maybe every 0.1 or 0.2 seconds. The spacing of the tennis ball tells us that as time goes on, the ball actually increases its velocity, because we can see over here that this first picture, the balls are actually overlapping. When we take the second picture or the second time frame, there's slightly more difference between them, and then slightly more difference, and then more difference. So because it is increasing the distance, even though it's the same time interval of each picture, it is falling at a faster rate. So that tells us that the tennis ball is accelerating. And the position time graph of this, since we see this graph or this diagram on the left, they are actually making the negative value positive, which I don't necessarily like, but we're going to draw an example of both. So if we have our position time graph here, they have it starting at 0.0 meters, going to 0.1 to 0.2 to 0.3. So our graph is actually going to be a curved upward pointing graph if we use the same data set that they provided. If we didn't use the same data set that they provided, our position time graph actually would look kind of like our velocity time graph, but instead of starting at 0 in the positive segment, we're going to start at 0 at the negative segment. And our graph's actually going to look like this. Okay, that's the way that my brain works. Right now, both of them are correct because it's starting with a slower velocity that is increasing as every time interval increases. Now for objects thrown into the air, we can see that this path on the right follows a curved trajectory. What that means is that as the ball goes into the air, it has a high velocity, it slows to the top of the path, and then has a increasing velocity as it falls back down to the ground. But the photos indicate that it is undergoing an acceleration because we do not have equal distances in between each photo of the tennis ball. The velocity changes in a certain way. So on this tennis ball, I'm actually going to draw the velocity vector arrow. So we have a relatively large vector arrow for the first ball. We have a slightly smaller one, and then slightly smaller and smaller, and at the very top, the velocity of this tennis ball is actually 0 for a small portion of time. Then a slightly bigger but negative, slightly bigger but negative. Now, the nifty thing about these is that if you have the tennis ball before and after, if it is at the same level off of the ground, the velocities will be equal but opposite. So if the ball here has a velocity of 10 meters per second, over here it has a velocity of negative 10 meters per second. So the question, how does the velocity change as the ball travels? It decreases until the top, and then it increases in the negative direction. So that's how the velocity changes. Well, what about the acceleration? The acceleration of this ball actually never changes. We will always have an acceleration vector pointing downward from this tennis ball because gravity is always trying to pull it to the earth. And this green vector, I'm trying to be very careful to draw it relatively the same size because the acceleration pulling downward never changes. We can't shut gravity off. If we did, everything would fly off the planet. So gravity never goes away. That tends to be kind of confusing, especially later in this unit, but gravity can never be ignored. Okay, so as the ball travels, the acceleration remains constant at negative 9.8 meters per second squared. Okay? So, free fall practice. Same math, same equations, same everything as kinematics problems. The only difference is now you know the acceleration. The observation deck of a tall skyscraper is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. So this does not give us very much information. But when we work on these examples in class, you have to look for a very specific word. If it says that something is thrown, that means it has an initial velocity. If it is free falling or just falling from a location, its initial velocity has a value of 0. So it's asking us to determine the time. We have distance, we have delta x or xi and xf. We do not know time, but we do know the acceleration. And since it says free fall, we also know the initial velocity. So over here I'm going to write our variables, xf, xi, vi, and a. We have 9.8 meters per second squared. I'm going to put a little negative in front. Vi is 0 meters per second. Xi we are going to use as 370 because it is starting at the top of the skyscraper, and xf is going to be 0. And our unknown is time. So based on these variables, we can choose that our equation is going to be the xf equals xi equation because we have or can solve for each of those variables. So xf equals xi plus vit plus 1/2 at squared. That's the equation we're going to end up using. So we have 0 equals 370 plus 0 times time plus 1/2, 9.8 with a negative, t squared. So this goes away. We have to get that 370 away from the rest of this component, so we are going to be subtracting. 370 equals negative 4.9 t squared. Divide out, and t squared equals 75.5. And get rid of that squared by square rooting both sides. And t is 8.69 seconds. So that is our final answer. It takes that penny 8.69 seconds to fall to the bottom. Now we have another practice problem. A baseball is popped straight into the air and has a hang time of 6.25 seconds. Determine the height to which the ball rises before it reaches its peak. First thing I'm going to do is draw the picture of the baseball flying through the air. So here is what it's going to look like. We're hitting it from this location, it travels up, and then falls back down. So there are a couple things that I do know even though it's not listed. I'm going to automatically write down VI, VF, AT, and we are looking for XF. Okay, now if we are starting from the second half of the path, let's say we're going to freeze frame here and only use the middle height or the height at the middle to the very, very end. I know that my VI at that top point is 0 because for a millisecond that ball suspends in the air and doesn't move. My VF I don't know. My A is negative 9.8. My time, they give me a whole hang time of 6.25 seconds. So in order for us to use that time wisely, we need to do something with it. 6.25 is this entire path. So if we ignore air resistance, we can assume that the time for just the second half of this path that we are looking at is half of that value. So my time is actually 3.125. And my other unknown variable is XF. I can pretend that XI is 0 because it's being hit from as close to the ground as possible. So since we are solving for XF, we want to use the same equation as before. XF equals XI plus VIT plus 1/2 AT squared. And we're assuming that XI is 0 and VI is also 0 at the top of the path, so these two values can completely be crossed off. So XF equals 1/2 negative 9.8 times 3.125 squared. And XF has a value of negative 47.85 meters. Now this value happens to be negative because we used the second half of this trip. So technically it was starting at XI being 0 and ending with XF being at the ground. So that's just a directional negative. If we are talking in terms of height off the ground, we are going to disregard that negative sign. Okay, so when you come back to class, we are going to be working on more of these examples and getting more in depth with free fall problems. Again, they're exactly the same math as kinematic equations. The only difference is you always know your acceleration or you're solving for it because you're on an unknown planet. See you guys soon.